Hello. We're going to start by talking about discrete time systems in general. We'll talk about signals, and then we'll morph into talking more about linear time invariant systems, convolution, and some basic filtering operations. When we're doing digital signal processing, the digital refers to two factors or characteristics of discreteness with a signal. So as you can see over here on the left, if we start out with a continuous time signal, if we want to do something with that on a computer, we need to first put it in a format that a computer can work with. And so that involves two operations. One, as you might recall from calculus, there are an uncountable infinite number of points between any 2 points on a line. Most computers cannot hold an uncountably infinite number of samples. And so we're going to instead take discrete samples, and we usually do this so that they're spaced evenly apart. And so we can see on this upper plot we have discrete samples, and we have indexed those by n. We could also have assigned the actual time value to each of them, but we'll find that the index works just fine. The other thing is the amplitude of each of these samples is a real number. Once again, real numbers are very hard to express accurately in a computer. Sure, we can express them pretty accurately, but not perfectly. So whatever we do when we put it into a computer, there is some discretization of the amplitude as well. So this lower one isn't quite that. This lower plot is showing discretization of the continuous time sinusoid, and then over on the right we have both discretizations occurring at the same time. That is, we have discrete samples of our signal, and each of the discrete samples has a discrete amplitude. Now we have something that we can store on a computer. Each of these samples could be stored in a single memory location, for example, and the accuracy of the amplitude of that sample would be a function of how many bits we can use to store it, and also the format that we use to store those bits. So we will spend most of our time here, but we really want to know how that relates back to our original analog signals. And spoiler alert, although you've probably run across this in an earlier course, if certain conditions are met, we can go from this discrete signal back to the continuous signal quite easily and very accurately. So that's what goes on in a computer. In this course, most of our time is going to be spent on this one. We'll assume that we have perfect samples. And if we don't have perfect samples and we're using a program like MATLAB, well, we assume that double precision floating point values can be pretty close to perfect, at least for our purposes. And in most cases they are. We will, however, spend a little bit of time coming back to discrete amplitude, discrete samples. So here's an example blown up of a signal that we might use. In this case, x of n represents the value of a signal at time n. And I'll put time in quotes because it usually, unless you sample 1 time per second, time n is not really a time. So notationally, our textbook uses square brackets for sampled or sequence data. And the textbook uses parentheses for continuous data or continuous arguments. I will try my best to be consistent with the textbook in this regard. I have noticed, though, that I try to write as quickly as I can so that you're not sitting here falling asleep while I'm writing. And the quicker I write, the more my square brackets look like anything but square brackets. So we will, but that's what I'll try to do. Square brackets mean discrete data, and continuous, or parentheses mean continuous data. So we showed as our first example a sinusoid, and then something that looked like it was exponentially increasing and decreasing and so on. Let's spend just a moment and review some of the common signals that we're likely to use. In fact, we use these quite frequently. The first is our impulse function. It is 1 when n is equal to 0, and it's 0 everywhere else. This is called a delta function, or Kronecker delta, or impulse. Multiple names. It shows up a lot. You might have noticed that the more something shows up, the more common it is, the more likely you are to have multiple different names for it. Okay, the next is the unit step. The unit step, it's easy to see from the plot to the left, is 1. For n is greater than or equal to 0. It's 0 everywhere else. And then we have something, those two have special names. We use u for the unit step and delta for the impulse function, or delta function, or whatever you want to call it. After that, it tends to be a little bit more generic. So with something like a real exponential, you get, we'll just use our generic x of n to represent the exponential. In this case, we have a value alpha to the n, and alpha in this case must be, for this example, alpha is going to be less than 1 because as n increases, the value decreases. It's very common to have something such as x of n is equal to alpha n times u of n. And what's that going to do? This will give us a function that is 0 up until n is equal to 0. So it's 0, minus 1, minus 2, and so on. 1, 2, 3. And at that point, we start to get our decay. And this is really nice because the u of n multiplied by that is essentially just multiplying 0 times anything that is on the left side of the real number line, and it makes sure that you don't have something that blows up. Okay, a sinusoid, another function that we will use quite a bit. This is a cosine. Omega naught would be the frequency times n, and then the phi would give us a phase shift. And we'll find out later that these are eigenfunctions of linear systems. And I'll talk more about that. If that means something to you, great. You're keeping right up. If it doesn't, well, my job as a teacher is to help you see how that does mean something to you, and we'll do that in a few lectures. Finally, everything we've looked at so far has been real valued, but having complex valued signals turns out to be very useful. And so in this case we might define x of n is equal to a some amplitude e j omega n, and here, as in the sinusoid above, omega is in radians per sample. And it could be that A is complex. Often if you're going to have a complex value there, for reasons somewhat hidden in history, a different value would be used, such as a capital X. Why is that? I'm not sure. But one thing to notice while we're right here is that what we have there, if we put our j out front, our j is the square root of -1. I'm running out of room. Let me scoot this over. There we go. We could get something like this. So let me finish putting this out. Using just the laws of exponents, we get 2 pi k n. And e to the 2 pi k n, I'm going to tell you right now that that is equal to 1 for integer values of k. And also for reasons somewhat lost in time and history, n and k tend to be variables that we use for integer values. And so when you see a k, at least in this course, it's going to be an integer. So why is that? Well, we can take a look here. It's because of Euler's identity. We won't be proving that in this class, but if you have e to the plus or minus j theta, that's just equal to cosine theta plus or minus j sine theta. And this is called Euler's identity. And if we look back at what we did just above, that would mean that this value here is going to be cosine of 2 pi kn. So 2 pi, it's going to be an integer multiple of 2 pi. A cosine of 2 pi is 1. Cosine of 4 pi is 1, and so on and so forth. Whereas a sine of 2 pi, or any multiple of 2 pi, is going to be 0. So indeed, using Euler's identity, we can see that that's equal to 1. And therefore, this equivalence is true for all n. Now, the other side of Euler's identity is cosine theta is equal to 1/2 e to the j theta plus e to the minus j theta, and sine of theta is equal to 1 over 2j e to the j theta minus e to the minus j theta. So where did these come from? It's fairly easy to see if you simply use Euler's forward identity, plug those into the j thetas here in the inverse relationship, and you can just work it out that it comes back that way. So there's nothing magical about this. It comes from the definition given above. Okay, a few other concepts that we should cover about signals. One is periodicity. So for a discrete time signal, we have a periodic signal if n plus capital N, which this would be the period, and it's also an integer, is equal to x. So if this is true, for some n and all little n, then we have a periodic signal. Okay. So one thing that I would like to point out right away is that if you have some signal, let's assume we had some continuous time signal, and just pretend that that's perfectly periodic. So here we have a periodic x of t. If we then come along and take samples of this signal, it may not be periodic. And so the continuous time signal being periodic does not imply that the discrete time signal is periodic. I imagine this works both ways. You could have some non-periodic version of x of t, but if you sampled it just right, x of n would be periodic. One possible case like that could be if x of t always hit a certain value at every second, but in between was random noise. The signal itself wouldn't be periodic, but if sampled at that exact 1 second interval, you would have a periodic signal. So, periodicity. Now, next we're going to get into linear time invariant systems, but as a first step for that, I would like to introduce one more thing that, whoops, that's the wrong one. Okay, there we are. So what you're seeing here is a speech signal. The continuous time version is shown up top, and the discrete time version is shown down below. You might think, how did we get this perfect discrete time or continuous time version shown there? Well, we cheated. We just connected the dots from the sampled version below because that's what we really have in the computer, is a sampled version. But you get the idea. We have this continuous time speech signal, and then we sample it. And so we started with x of t continuous time speech, and now we have x of n, and we're going to talk more about sampling later. But the first thing we're going to do is work out a new way to write this. As x of n is equal to the sum delta n minus k x of k. Well, x of k and x of n are the same function. They're just indexed by different inputs, one by n, of course, one by k. And the delta, we've seen that before. So what can we tell by looking at this? Well, for one, delta of n minus k is equal to 0 everywhere that n does not equal k, and it equals 1 when n is equal to k. So we can see that this function then is almost trivially true. Since we're multiplying the value, the sum on the right, every value of x of k is being multiplied by 0 unless k is equal to n, then we have, yes indeed, written down essentially x of n is equal to x of n. So what use is the thing on the right? Well, we'll find out more what it's useful for next time, and it really is useful. But I want to show one other thing related to this and just what exactly is going on. It may help if we deal with a little bit simpler signal than the one up above. Let's assume we have this signal at 0 most places. At 1, 0, 1, 2, we have values like that. Value of that's 2, that's minus 3, and that amplitude is 1, and then it's 0 everywhere else. Well, we could write this graphically as 2. All the rest of these are zeros. And add to that minus 3. And a bunch of zeros everywhere else. And add to that our 1 in the correct spot with zeros everywhere else. And when we sum up all these values, it's a lot more work, but we get let's see, we sum up zeros in the columns to the left, and we have 2 plus 0 plus 0, that gives us a 2 here, and then 0 plus minus 3, I didn't give myself a whole lot of room, I'll just write minus 3 plus 0, and then we have 0, 0, and 1. So sure enough, what we've essentially done is we've said this sequence, or any sequence of samples, can be looked at as a sum of a whole lot of sequences. Each sequence is a single sample in and of itself. So in this particular case, this is delta of 0 times x of k, or x of 0. And this is delta of, I'm sorry, I misspoke. That's delta of n times x 0. This is delta n minus 1 times x 1. And the last one would be delta n minus 2 times x of 2. And x0 is 2, x1 is minus 3, and x2 is 1. So we've essentially expanded this out into its component parts. A lot of work in the meantime, but in practice we never end up actually having to do this. This is just going to be a tool that we will use to analyze linear time invariant systems going forward. Thank you.